Hi everyone, Mr. Neighbor, and we're talking about acceleration specifically with free fall. So recall, free fall is when you're falling with only gravity as the force acting upon you. So you're falling at 10 meters per second squared. So what happens if we start by throwing an object up first into the air? What's its velocity is going to be every single time it only has gravity acting upon it? So remember, free fall, we're accelerating at 10 meters per second squared in the downward direction. So every second that passes, I'm going to be pulled faster downward 10 meters per second. So if I was flying up at 20 meters per second, after 1 second, I'm going to be pulled 10 meters per second down. So I will still be moving in the upward direction, but not as fast. I'll only be going up at 10 meters per second. Another second later, I am gaining velocity in the negative direction, 10 meters per second. So at this point, I will be at 0 meters per second. 1 second later, I'm going to gain another 10 meters per second downward. So if I was at 0, now I'll be at 10. Now it's downward finally. And then 1 second later, I'm going to gain another 10 meters per second downward. So it's going to be 20 meters per second. So at 2 seconds after you throw this object into the air, it's finally going to stop and then start to come back down. But until that point, it's going up. After that point, it's going down. And we can see that because of the negative in front of the velocity. All right, so let's continue to look at free fall. Let's drop an object and see how far it falls as time passes. All right, so let's look at first the average velocity part of this table, and we'll work our way through the distance traveled part. So remember, average of anything, you add the things up and divide by how many you have. So we want the average velocity during the second. Having a hard time talking right now. So during this second change, I have to add the velocities up and divide by how many I have. I have 2 velocities here. So add those together, I'm going to get out negative 10 divided by how many I have? 2. So negative 10 divided by 2 is negative 5. So the average velocity in that time frame is negative 5. Now let's look at it again. Next one, in this interval, I have 2 velocities. If I add those together, it's negative 30. Divided by 2, that would give me out an average of negative 15. Do it again. These two, 20, 30 is 50, divided by 2 is 25. And do it again. Oops, right here. 30 plus 40 is 70, divided by 2 is 35. Notice I'm not saying the negative, but all these are negative because they're still going down. All right, so now let's look at the distance traveled during the second. So during the second, we are averaging 5 meters every second. So that means in 1 second, we're going 5 meters. So the distance traveled is 5. Notice it's distance, it's not a vector quantity, so I'm only writing it as a magnitude. Then for this section, we are traveling 1 second, and we're averaging 15 meters per second. So in 1 second this time, we're traveling 15 meters. Then in this second, we're averaging negative 25 meters per second, so we're going to go 25 meters. And then lastly, 35. That's why we looked at the averages first. If you just look at the instantaneous velocity, it doesn't tell you what happened over the period, it tells you what happened at that moment right there. So we needed to look at the average. Now let's find the total displacement from the top. So remember, we're starting at 0. Let's pretend we're starting at 0. So we first progressed 5 meters, but we're going downward, so I need to include the negative. Then we added 15 on top of that, so that will be negative 5 plus negative 15, which is negative 20. Now we add negative 25 on top of that, so that would be negative 45. And then we add 35 on top of that, which would be negative 80 meters. Making a chart, as we just did, is very good to help you understand how the distances are calculated when talking about free fall. However, it's not practical to do that for every single situation. So there's a formula that we can use to model that table instead. That formula is the change in position, or the displacement, is equal to the initial velocity on average plus 1/2 the average acceleration. So if we just do the very, very last example with that, actually, there's some examples to follow. I'm not going to do that. Okay, I lied. There isn't any examples following that. So we're going to do the one above really quick. So the very last time was 4 seconds. So that's what we're going to use. So the initial velocity, not the average velocity. I made a mistake there. It is just the initial velocity was 0 meters per second. We weren't moving. That time we were looking at is 4 seconds later. Take 1/2 times the average acceleration, which is negative 10 meters per second squared, times 4 seconds later again, squared. Squared is part of the formula. So when I finally calculate this, I'll have this as 0, 4 squared, which is 16, half of negative 10, which is 5, and 5 times negative 16 will be negative 80. Our label should all cancel out, because notice seconds squared will cancel out with seconds squared, so I'm only left with meters. And that's the exact same answer we got out for our above problem at 4 seconds. So when you're doing acceleration problems, go about it by looking at what you're given. So you have a couple different formulas. You have the very first one, which we learned about, which was your average acceleration. Then we have our final velocity formula. And then we also have our change in position formula. And you also can think about it conceptually. You don't need a formula. You can think about acceleration as this much speed being added on or taken off every single second. You can do it like that. Don't overcomplicate it. Okay. Remember that when you accelerate, your velocity is changing. Either the number of your velocity, the magnitude, or the direction, because velocity has both a magnitude and a direction to it. So a lot of times we talk about linear motion, which is in meters. The velocity is in meters per second, and the acceleration we will use will be meters per second squared. But if you're ever doing things in a circle, going around a curve, spinning something, then we're talking about angular displacement, which is talked about in revolutions or radians. We're going to be talking about the revolution part. When you get to physics, you'll talk about the radians because you'll have the math for that. Angular velocity is how many revolutions something does every single minute. So how many times does it go around in a circle in a single minute's time? Does it go around 50 times every minute? And angular acceleration, we talk about this in revolutions per minute per second or radians per second when you get into physics. Okay, we won't talk about this much, but the thing I really want to talk about and point out is that there's different types, and a very special type of acceleration is called centripetal acceleration. It's not the spinning part, it's not the acceleration going this way, it's the acceleration that's keeping the ball going in a circle. So centripetal acceleration is what I'm really concerned about you understanding. It's a center-seeking acceleration. It means the velocity is changing because the direction is constantly changing. First the velocity is going this way, then the velocity is going this way, then the velocity is going this way. It's always changing velocity, so there is an acceleration. And that acceleration is keeping the people attached to the wheel. It's the road pushing the car inward. It's the string pulling the rock toward the middle. Centripetal acceleration is center-seeking acceleration. A lot of times people confuse centripetal acceleration with centrifugal acceleration or force. Centrifugal force doesn't actually exist. It's really inertia. So only think about centripetal, not centrifugal. Only centripetal, the center-seeking acceleration.